All right. Okay, so here we go. So honestly, this is probably the last section of notes I'm going to do. Section 2.4 is all just about graphs. And I don't know that I need to lecture on it. I think you guys just got to kind of work with it, and you'll kind of figure stuff out. And if I'm wrong, then we'll do clean up on the back end. But I think you'll be okay. All right? So here's the deal. We learned in the last section that if you know the position, if you know an equation for the function of position as a function of time, that you can take the derivative of that, find the velocity, and take the derivative of that, find the acceleration, right? Well, it turns out we can also go backwards, okay? So if I give you the acceleration, we can work backwards to find the velocity and work backwards from there to find the acceleration, okay? And doing that requires using what's called an integral, all right? An integral is often called an antiderivative, okay? So I know a lot of you guys are not going to get integrals in calculus until, what's that? February? Okay. So not for a while, all right? I'm going to teach you very, very, very basic integrals, all right? And so basically the question is this. When you're taking an integral, the question is, what do I have to take the derivative of to get this thing? Does that make sense? So instead of starting with a function and finding the derivative, you're starting with the derivative and figuring out what you took the derivative of to get it. Make sense? So you're just kind of working backwards. And honestly, in calculus, you're going to learn all these tricks and stuff. Most of the integrals we're going to do in here are going to be very simple. Okay? So with that in mind, let's kind of move forward and see if we can figure this out. Okay, so. All right, so suppose I gave you the following graph. And you wanted to find the displacement between 2 and 7 seconds. All right, so before I say anything, make some observations to yourself about the graph. All right, so we're going to go no cards here. Let's see, Molly was on the hook last time, so we're going to talk to Zach. Where is Zach? Oh, he is. I forgot to mark him absent. Wow, that was lucky. I totally forgot to take attendance. Okay. All right, so Hunter, help out. Tell me something about the graph. Sorry, I wasn't trying to catch you off guard. Your name just happened to come up.
Hi.
So tell me something about the graph.
Flat.
Okay, what does that mean? Which means what? Let him think. It's okay. I wasn't trying to catch you off guard.
Wait. Okay.
Okay, so what kind of graph is it?
Velocity. Velocity.
Acceleration is 0. I'm sorry, Hunter. Hi, I'm Mr. Hecker. I'm an asshole who just totally caught you off guard. I really wasn't trying to, honestly. All right. Okay. Oh, that's now on YouTube. Okay. Anyway. Okay. So, all right. So you said the acceleration is 0, and you know that because
the velocity is not changing.
Yeah, the velocity is constant, right? All right. So, what is the velocity, you guys?
0 meters per second.
Is it 0? It's 3. The velocity is 3. Because look, 1, 2, 3. The velocity is 3.
That looks like
right?
It looks like a 0.
Oh, I see. Okay, right. I gotcha. Okay. Because the line is. All right. Okay, so the velocity is 3, right? So, to figure out how far it goes between 2 and 7 seconds, we should be able to do this. Let's see. Velocity is constant at 3 meters per second. So, displacement is velocity times time, right? We're traveling at 3 meters a second for 5 seconds. That means we're going 15 meters, right? Good. All right. Notice, all that did though, it did not give me the position. It gave me the change in position. Right? And I don't know what the starting position was. I don't know where this thing was at the beginning. But I'm still able to figure out how much the position changed by. Okay? Now, in the same way that derivative has a conceptual meaning, like if you look at a graph, when we find the derivative of that graph, what are we really finding? I heard a couple people say slope, right? The slope at a point. right? So conceptually, derivative means slope. All right? Similarly, integral means area. Okay? So down here it says, notice that this is the same as the area between the curve, the v of t curve, and the x-axis. In other words, look, we were trying to find the displacement between 2 and 7 seconds, right? So how much time elapses there? 5 seconds, right? So if you picture this rectangle here that is boxed out vertically by my time bounds and horizontally by the graph and the x-axis. So let's see, this side up here, the side of this rectangle would be 3 meters a second. So if you picture this green rectangle here, how do you find the area of a rectangle? Base times height, length times width, right? So it's 5 times 3, right? Make sense? All right? So as we move forward, we're going to make a connection between integrals and area between the curve and the horizontal axis. Okay? That's what the integral conceptually means. It gives you the area between the curve and whatever your horizontal axis is. For us, that'll almost always be time, with one exception. Follow?
Yep.
Okay, so let's do another example. Let's not do another example. Let's do this using calculus. This is going to be a little bit weird. All right? So, all right. What's up?
So, sorry, unfortunately.
2.3?
The answer key number 4 and B are wrong.
Oh, are they?
Just like
Okay. Possible. Very possible. Sorry. It's a problem with me writing my own assignments.
Okay.
Okay, all right, so here's what we're going to do. So we're going to use what's called, eventually we're going to switch over, and we're pretty much going to always use definite integrals, all right? But I think that to fully understand definite integrals, we got to talk about what are called indefinite integrals first, all right? So here's the idea. Look, my goal is we're trying to find the displacement. So I want to find my change in x, right? Okay, which is related to position. And what I know is this. I know that my velocity equation is just this, right? Isn't that the equation for my velocity function?
Yes.
Follow? All right, so there should be some equation for position. Let's see if we can come up with an expression for position. All right, I don't know what it is, but here's what I do know. I know that whatever that expression for position is, if I take the derivative of it, I got to get this. Does that make sense?
Yep.
All right? So I don't want to write this down, but you might want to. So to find our position, we're going to take the integral of v of t. That's the way you'd say it. Take the integral of the velocity function. All right? Doing that is exactly the same as saying the derivative of what is 3. Follow?
Yes.
Okay? So, position as a function of time must be, well, what thing can I take the derivative of and just get 3? 3t, right? Hold on, I know some of you are ahead of me, I got you. We'll get there. Do you guys all agree that if I take the derivative of 3t, I'm going to get 3? Good? Okay, but the problem is this. That's not all of it. Because what's the derivative of a constant? 0. So there could be a plus, and I know in calculus you use c, right?
Yeah.
Okay. For us, it has that c has meaning. It turns out. Shoot! Do I want to go? You know what? I'm going to use c for now.
yes.
I'll stick with c. All right. So does that make sense? Right. So now, if I take the derivative of this. The derivative of 3t is 3, the derivative of c is 0, so the derivative would give me 3. Follow? All right. Really briefly, in this example, here's why I'm hesitating a little bit. It turns out that in this example, that c is just your initial position. right? Because I put zeroing for t, then you get your initial position, x0, right? All right, so, yes.
How do you know C, or are we not doing that yet?
We don't know c. We just know there could be some number there, we just don't know what it is. So we're kind of like, crap, there's some number, I don't know what it is, let's deal with it, okay? So, but it turns out that it usually won't matter, okay? Because remember, we're trying to find the change in position between t equals 2 and t equals 7, right? So, let's do this. Let's find our position after 2 seconds. Well, that's 3 times 2 plus c. So that's 6 plus c, right?
Yep.
Similarly, our position after 7 seconds is 3 times 7 plus that same c, which is 21 plus c, right? So let me pause there for a minute. I know you guys are racing to write that down. Good? Very good?
Yep.
Once, twice, sold. Okay.
Oh, never mind. You just did it. We're good.
You good?
Yeah.
So, to find my displacement, I'm going to find the change in position, right? So I'm just going to subtract these two things. And watch what happens. I'm going to have 21 plus c minus 6 plus c. Don't the c's cancel? And you just get 15. So the c's don't matter. All right, now, this was a really stupid way to solve this problem, right? Okay? But I want you to understand that what we did there, we used a really complicated method. We took an integral, we undid the derivative, we took an antiderivative to find an expression for our position as a function of time, and then found the change in position. Cool? All right. So what we did here, this process, where we ended up with this, because we've got this plus c here, we used what's called an indefinite integral. Indefinite integral. Why do you think it's called indefinite? It's not defined. We don't have a definite answer. We got the stupid plus c here. Make sense? All right? So maybe a more efficient way of doing this is to take what's called a definite integral. And it basically boils down to the same thing, except you don't have to worry about the plus c, because we know that it's going to subtract out. Follow? So, option 3 is we're going to do the same thing, but we're going to take a definite integral, and we're just going to not worry about the plus c. All right? So, here's what we're trying to do. So, we know that our velocity as a function of time is 3, right? So, I know that if I take an integral, it gives me position, right? The definite integral gives you the change in position. All right, so our change in position is, and I'm going to introduce some new notation. All right, so derivative, you do like df dt or dy dx or whatever, right? Okay, the symbol for an integral is, it's like a stretched out cursive s, or not cursive, stretched out s. Okay, but it's supposed to be a little bit taller than your letters and numbers, you know what I mean? Okay, so we're going to take the integral of v of t. So this is fancy speak for the integral of v of t with respect to time. So we're going to put a little dt here. Basically, this just tells us what our x-axis is. Remember I told you that it's the area between the function and the x-axis? This is telling me what I have to put on the x-axis to find my area. Okay? All right? So, what two x values do I want the area between? like going back to this picture, what two x values do I want the area between? 2 and 7. So the notation you use is this. You put a 2 here to indicate that that's the lower x value you want to take the area between, and 7 is the upper value. All right, so all of this notation basically just means what's the area between the velocity of time function and the t-axis between times 2 and 7. Cool? The important thing to notice, you guys, is that when you take a definite integral, it gives you the change in the quantity. Okay? It gives you the change. Does that make sense? So if you take the integral of if you take a definite integral of acceleration, it doesn't give you velocity, it gives you change in velocity. Okay? So a definite integral always tells you the change. Follow? Yes.
So the indefinite integral.
Correct. The indefinite integral gives you an expression for the actual position instead of the change in position, but with the caveat, I don't think I've ever used that word before, I don't think I'll ever use it again, that we don't know what the c is, right? So we're kind of stuck because I'm recording, right? Good? All right. So here's what we're going to do. So this is the integral from 2 to 7. V of t is 3 with respect to t. So this is now asking us, what thing has an integral of 3? So what you guys said before. What thing has an integral of 3? 3t. And we're going to not even worry about the 3. So you get 3t. All right. So now I've taken my integral, right? Because the integral of 3 is 3t. Don't worry about the plus c, because we know it's going to cancel out anyway. Follow? And then the notation we use is this. You draw a vertical bar over here, and just write between 2 and 7. So this means evaluated at 7, evaluated at 2, and then just subtract. I think once you get the hang of this, this will not seem nearly as complicated as it seems right now. It's a little overwhelming right now. You'll get there. Sarah, what's up?
What is the d next to the 3?
This dt, it's telling you what you're taking, so that the technical way of saying it is it's telling you what you're taking the integral with respect to. In English, it's telling you, remember I told you that the integral was the area between the curve and the horizontal axis? This dt is telling us what has to go on that horizontal axis. So the d doesn't really sort of stand for anything, it's just notational. If you wanted, the d kind of means with respect to.
Okay.
Does that make sense? It's telling you what goes on the horizontal axis.
Okay.
Follow? So it's sort of like a math grammar thing to clarify.
Okay.
Cool?
Yep.
Everybody okay? Okay. It's kind of, if it helps any, Sarah, I don't know if this helps any. Yesterday we did a lot of this. We did, let's take the derivative of x with respect to t, right? It's the same dt. So this, weirdly, the top d here means the derivative of, and the bottom d means with respect to. Okay, I know, it's weird notation. That's honestly, the notation is kind of the hardest part of a lot of this. And once you get used to it. All right. So all I'm going to do now is I'm going to plug in 7, I'm going to plug in 2, and I'm going to subtract. So this just means 3 times 7 minus 3 times 2, which is 21 minus 6, which is, once again, 15 meters. Bless you. Okay, that was a lot all at once. Here are the big takeaways that you need to have. Okay? Taking derivatives, I think you guys are good with, right? Derivative of position is velocity. Derivative of velocity is acceleration. Okay? If you want to go the other way, the antiderivative, sorry, no, I don't want to say that. The indefinite integral of acceleration is velocity, and the indefinite integral of velocity is position. Okay? But because it's indefinite, that often doesn't help us much. Okay? So what we'll use more often is a definite integral. in which case the definite integral of acceleration isn't velocity, but it's change in velocity. And the definite integral of velocity is not position, but change in position. All right? There is a graphic at the end of the notes that summarizes all of this. I wasn't going to show it to you till later, but since we're running out of time here, right there. So derivatives and integrals. So position, if you take a derivative, it gives you velocity. If you take a derivative of that, it gives you acceleration. Good? If you start with velocity and take a definite integral, it doesn't give you position, it gives you change in position, right? And taking a definite integral of acceleration gives you change in velocity. All right, and I guess if you wanted to, you could add in, well, we don't have time, but you could add in indefinite integral would be pointing up this way. Cool? All right, we will pick up there tomorrow. Hang in there. All right?